Today's seminar is about the JPAS, which is a survey for galaxy evolution studies, and will be presented by Dr. Rosa Delgado, González Delgado, sorry. And she's a research professor in between CSIC, which is the highest position. She's working in our institute in IAA since '98, and around the line of research on galaxy evolution. She also is working in Stardust AGN, working on data from in the optic and ultraviolet from the Hubble Space Telescope. And now she's working on JPACE and for the exploitation in the survey for the study of evolution of galaxies. So, Rosa, thank you for the seminar, and it's yours. Thank you.
Okay, thank you very much for coming to the seminar. It is a pleasure to be here and explain to you what is JPAS. Also, you know, most of you know about the survey. But in particular, I want to focus about the status of the project now, and in particular of the relation of the status of the project for galaxy evolution study. Of course, I had to thank first to Mariano Mole, who is here, not only for coming, it's because he is really the alma of the project, together with Chicho Benito, that unfortunately he cannot be here. There is also many people from the collaboration, including the people that are working here at the IAA with me, but also I had to mention the people in the Galaxy Evolution Scientist group, that we every week we have a telecom to discuss the progress of the project and the interest of our interest in the science that we can be done with this beautiful instrument. Okay, so let me give a brief introduction about the JPAS. JPAS is the name of Javalambre Physics of the Accelerating Universe Astrophysical Survey. The idea was to measure the BOA. For that, they built the telescope at the Javalambre Observatory, and the idea is to do a photometric survey of 8,000. Now is more like 5,000 square degree of the sky. This is a panoramic of the observatory. Well done, the photograph, because there are no clouds. That's the first condition to make a photograph of any observatory. And they have a 2.5 meter telescope, which is the telescope for the project. This is the telescope, and they have a camera, which is the GPCam. This is the GPCam. They have a 14 CCD, and they cover a field of view of about 3 square degrees. One important aspect, which is really good for a study of galaxy evolution or for research in galaxy evolution, is the system of filter that they have. And they had a 56 filter, narrowband filter, which is separated in wavelength every 100 angstrom in the central wavelength, and we can cover for the almost the near ultraviolet to the near infrared. In this way, we can sampling quite well the distribution of the optical, the observed optical wavelength of any object, galaxy or quasar or star in the sky. That's really very important if in fact it can retrieve the property of the object. This is the status of the project. Was announced at the beginning of September. We are now in the phase where it is finishing most of the technical aspect related with the GPCAM. It is expected that for beginning of the year, in January, they will have the first light of the camera, and during the up to June, they will do the technical and scientific commissioning. So it is expected that in less than 1 year, the camera will be fully operating, and we are starting, in fact, the scientific operation of the project. But that does not mean that we don't have any data at all for this project. We have already taken data for several fields with the Pathfinder camera. The Pathfinder is only a CCD. Instead of the 40 CCD that they have the GPCAM, they have only one CCD, and they have about 0.5 degree by 0.5 degree. This is the field of view that we can see. And during the last year, we were taking data in all the filter, all the filter system that we have for 4 pointing of the Aegis field. This is the 4 pointing that we are taking. The internal release of this data was done in April of the year, and from the last 6 months, we were working on the collaboration very hard to try to understand the data and to check which is the quality of the data. Of course, it was a lot of work for the UPAC, which is the unit that has the responsibility to calibrate the data and deliver it to the community, which is in the CESCA Institute. So we have to thank a lot to the strong effort that CESCA is doing, not only for perform the observation, but also for taking care of the data relation and provide to us scientific data. In addition to this 4 pointing that we are working on already, we have an observation from another cosmological field, which is the James Webb Space Telescope North Elliptical Pole, which is also covered 1 square degree in all the filter. And there is also some additional observation that at this moment we don't know exactly how many we have, because they are still finishing this observation and the data reaction, which is related with the Alhambra 8 field in several filters, the galaxy cluster Hercules, and also some nearby galaxy in the Khalifa sample, and also big galaxy from the local volume as it is M33 or NGC 4003. There will be the first public data release. They will be at the beginning of December during the RIA meeting, the Universe in 56 color, signed with the first GPAS data. There we will be delivered to all the community, so everyone, even if they are not member of the collaboration, can access to the data and to work with the product. Of course, the data will be delivered, calibrated, and also the catalog where they will provide the photo C for this galaxy. So it is expecting that at this meeting, everyone that it is interested in to make some exploitation of this data come to Teruel for this meeting, and there they can have a general idea of the quality of the data and how to access to the data. Okay, this is one example of the quality of the data that were internally delivered the last April. And here, that's the pointing, the 4 pointing. The quality of every pointing is different. In fact, the pointing number 1 is look like that it is the best one with the better C. But here you can have an idea, which is the magnitude limit obtaining in every filter. I was expecting we can go in fainter magnitude in the blue filter than in the red one. But in fact, this is a very, very good result. That's to announce the web page where you can retrieve the data. This is a real images in the field of ages. This is the list of table where you can access the result. So there are many ways that has been measuring the magnitude of the flash of the object in the survey, and also they will provide the table with the photo C, and we can make some cross match with different survey. And in fact, I was working this with André de Amorim in Brazil, in Florianópolis, to cross-match this catalog from the ages field, JPass data, also with the other survey like DEEP2 or Sloan, JPlus, and also the Alhambra survey, to be able to compare the quality or confront the data that we have. This is in fact one comparison of the data. The black dot and the red dot are the JPass data. And also in gray, it is the spectra of a Sloan for this galaxy, but in magnitude. Also, it was a scaling to make the R band equal. So that means that you can see that the JPass data can follow quite well most of the spectral characteristics of the galaxy, including, of course, the emission line, the H-alpha in nitrogen 2, and also the sulfur 2 line. This is, of course, this is a very bright galaxy. This is real nearby galaxy. It is a RESI almost 0.1. But here it is like a sequence in terms of RESI from this nearby 2 galaxy to this one, which is a RESI 1. And that's the data that we have. Notice that the magnitude is almost 20 for this galaxy in the R band, and this is another example for one quasar, which is a RESI 1.6. A more quantitative way to compare the data was done comparing the color in the I minus R color in the JPass with respect to the synthetic color that can be obtained from the spectra. And in fact, this result indicated that there are no significantly biased, but this comparison would be possible to be done, and of course you can see here they are well correlated. But this comparison has been done for only a few hundred of galaxies for which there is a Sloan spectra. It was better to do it with the photometry, for which there is in common the cross match between the Sloan and the JPass give us almost, I think, around 20,000 of objects. This is the comparison. Here we compare the G minus R color, the difference between the JPass and the Sloan, and here it is the comparison for the I minus R color of JPass minus Sloan. You see that there is the red point is the average value of every interval of magnitude. You see that they are almost a 0, so that means that there is no any bias of in terms of color between the Sloan and the JPass. This is interesting to know, because to have well calibrated the color of galaxy, it is important, in particular, if we want to estimate from the spectral energy distribution the property of the galaxy. Also because, after all, we have made the calibration with the star in a slow, so that means that the calibration that has been applied is really correct. Other important aspect related with the project is the comparison with another survey that are even deeper than the JPASS. So this is something that has been done by Luis Diaz, because he is working in the Subaru survey, one of the Subaru survey, which is very deep, and they include 5 broadband filter, which is the slow one, and what he has done is to compare, which is I'm plotting here, which is the fraction of galaxy that are in the JPASS and the Subaru survey. So, and they plotted as a function of the magnitude of the galaxy in the R band. You see that this is there are 4 curves. Each one corresponds to any of the 4 pointing that we have in the survey. That's for extended source. This is for point source. You see that we can that in JPASS it is detecting about 90% of the galaxy with magnitude around 23 for the ages 1, and for the other tile it is about 0.3 magnitude fainter. So, but that means that for this object, for this observation that we have already taken, comparing even with the survey, which is deeper than the JPASS, we have detected, or we are complete in a sample that for magnitude around 23 or 22.7. This gives us a lot of galaxy where we can study and to be sure that the sample that we are studying is complete. Group, and in particular for my intern. Also, we can consider JPASS as a survey later, the different aspects, including result that we have preliminary result, by result from the AGS field that we have obtaining. There is, let me to say that in galaxy evolution we can affront the study in 2 different ways. One, it is related with the study the property of the galaxy or the galaxy population and how changing this with the resid. The other is making a look-back time study. So that means that we are using the fossil record of the stellar population to go back in time and to know how was the star formation history of the galaxy and how the galaxy has grown their mass. So JPASS gives the opportunity to us, in fact, to do the study, these 2 types of studies simultaneously, because we can build very unbiased sample covering at least from very near galaxy to RESIC 1. And this is something that cannot be done for many of the surveys that actually are. Well, let's start with the first point, which is related with the cosmic evolution of galaxy property. This is a sample of result that has been already obtained for the study of the galaxy with the RESID. We know that the star formation rate density has a maximum around RESID 2 and has decreased from then to now in almost 1 order of magnitude. We already know that there is a correlation between the star formation rate of the galaxy and the galaxy mass. This is what it is called the main sequence of star formation. And this correlation That happens or not only a RESI in the nearby universe, but also a high RESI, up to RESI 2. We have checked already. So that means that this is an example of the property that we can retrieve from the JPass. I mean, we can study the star formation rate, the mass of the galaxy, and we can do for different samples of galaxy according with the RESI. The other is, as I mentioned before, is the fossil record method of the stellar population. In that case, what we do is to study, well, so far the spectra of the galaxy, and from the stellar feature, we can retrieve the stellar population that has already born in the galaxy. In that way, the luminosity of a galaxy can be modeled as a combination of the different births of star formation that has happened in the galaxy in the past. Of course, because we have a very narrow filter, and we can sample every 100 astro, we can pick up many of the stellar features, in particular all the Balmer break, but also some of the line as the magnesium or the calcium triplet, which is visible in the spectra of galaxy. And this can be used for retrieve, which is the mass that has been converted into a star in every epoch in the past of the galaxy. This is one example that we have done with the CALIFA survey, where we have estimated the star formation rate density. This is the black dot that's coming from CALIFA, and also this the star, which is compatible or comparable with the RESI study. We have also obtained, which is the how it is evolving the specific star formation rate, which is the ratio between the star formation rate of the galaxy with respect to the mass of the galaxy as a function of loopback time or RESI, which is equivalent. That's something that has been done for the CALIFA survey in the thesis by Rafael López Fernández. But of course, when we compare with the cosmological survey, there are some discrepancies, in particular when we go to upper RESI, to the higher RESI, because at that time it's very difficult to distinguish if the ages of the stellar population is 10 gigayear or 12 gigayear. If we do this exercise with the CALIFA galaxy, which is nearby galaxy, but if we can apply this method for galaxy, which is a RESI higher, the discrepancy or the degeneracy of the ages, it is smaller, and we can follow better the path of the galaxy. And this is why we were involved in building a new code for retrieving the star formation history of the galaxy by using the JPass data. In that case, we are modeling a parametric star formation history. This is a Bayesian approach where we can retrieve, we assume a star formation history, and we can estimate the mean value and also the PDF of the main parameter that it is described in the star formation history by fitting the magnitude in the 56 filter. That's one example of the. We have modeling. We can model in this galaxy assuming an exponential law, a delay tau model, and also a Sandwich model or any other. That's an example of the simulation, the input parameter of the simulation that have performed to be able to constrain, which is the precision for which we can estimate the parameter of the stellar population. I mean the mass, the ages, and also this value, the T0 and tau. Notice that T0 represents the point where started the star formation. And tau, for example, with respect to the delay tau model, is the time at which happens the maximum of the star formation. So that means that if we can retrieve from the magnitude, observed magnitude fitting with this model, we can make some estimation on how the galaxy has formed their mass and which is the epoch in which happened the maximum of the star formation. That's the result of some of the result of this simulation. It is the difference between the mass in the output by the code and the input value, and in the simulation, and you see that there is no barrier, and we can make a precision with less than 0.1 dex in mass. In similar way, we can make an estimation of the value of the T0, the onset of the star formation, and the tau, which is how broad is the star formation in time. This ratio can be estimated also with the precision of 0.3. So that means that even we don't have a spectroscopy with JPASS data, but it is almost can give us results that in some way are similar to the spectroscopy. Let me, before to go ahead, explaining this figure of merit, because we have used this figure of merit to try to understand the quality of the JPASS data. In a simulation, it is expected that the difference between the magnitude, the observed magnitude, and the fitting magnitude divided by the error has to be around 0. That's the result of the simulation. If we calculate this, this is what we call the normalized residual. If we calculate the standard deviation of this normalized residual, it is expected to be around 1. When we do this for our data, if it is not around 1, that means that in some way the error has not been estimated correctly for the data that we are analyzing. Okay, so that's a sample for galaxy also that is representing a sequence also in redshift and also in magnitude, going from the brighter one to the fainter one, and also from almost for different redshift. Okay, look at that many of these galaxies around the position of the expected H alpha line, it is clearly over the fitting, which is the red point, and that's indicated that in fact this galaxy has a sun emission line. That's happening in the 4 case. Because we can mask this emission, we can fit the continuum, and the difference between the continuum and the observed magnitude clearly can give us an estimation of the flash of the line. Anyway, going back to the figure of merit, this is the result of fitting almost 5,000 galaxies in the Aegis field. And this is the normalized residual. This is close to 0, but not too much, not exactly. But the difference, it is more or less in the dispersion, it is related with the mean value of the error that we have. And also there here point, as said before, there has to be around 1, it is over 1. So that's this tells us that in fact, in some way, the error in this previous data internal release were not estimated, I mean, they don't take into account all the effect. We know now from a few days ago that the UPAC has, they are continuing working to improve the data and the result, and they tell us that the error now are calibrated in a better way, and we expect it to be around 1, this figure of merit. Let me start also with another result related with the stellar population property of the galaxy. That's again 2 examples. This is one galaxy, this is 0.3, this is 0.47. Here it is a red galaxy. There are not really emission line any at all. This emission line galaxy, you can see also the detection of the oxygen 2 line and also the oxygen 3 and H beta. Okay, well, for fitting all the observed magnitude, except those that are masked due to the presence of emission line, we can estimate it, as explained before, the T0, tau over T0. Look at that, there is a bimodality. I was expecting, because that means that there are galaxies that are already quiescence, where it is expected that the tau over T0 has to be smaller, and galaxies where they have performed their star formation for longer period of time. So in that case, tau over T0 has to be even similar. What that means that the galaxy has a star formation which is continuing time. Okay, that's a very preliminary result. We are working on this. This is another result related with between the color in the data and the mass of the galaxy that has been obtained by Luis, where we can see the position in the diagram of the star-forming galaxy and the position of quiescent galaxy. Let me to explain now why also JPASS is a very interesting survey for emission line galaxy. So far, most of the survey are related with the spectroscopy or related with narrowband filter, but only 1 or 2 filters. With the spectroscopy, we have, this is the one example from the gamma survey, where they have the spectra up to 8,000 angstrom of galaxy of magnitude brighter than 20. And from measuring the line, we can build the BBT diagram and to discriminate between the star-forming galaxy or AGNs. Which is the limit of this kind of, what is the problem in general related with this survey, is because they are limited in the sky area, because they have to use a spectroscopy and to use fever for playing in the object, in every object, and also usually it is limited in magnitude. As happened, you see this is the limited in this long spectroscopy survey, and this is for the gamma. If we go for narrowband filter, as for example the survey in the Subaru, they have also the problem that it is limited in the area of the sky, but they have also the limit that they are using only 2 or 3 as maximum of narrowband filter. So that means that the can pick a galaxy that for the RESI they have the H alpha, for example, or any oxygen 2 or H beta at this wavelength. So that means that these servers are limited also in RESI. Does not happen with the JPASS, because we have the continuum filter from the near ultraviolet to the near infrared. We can pick up a galaxy at every RESI, so we are not limited in RESI. Of course, the only thing is that if we are using H alpha can be observed with this survey up to RESI around 0.4, but if we use, for example, oxygen 2, we can go up to RESI over 1. And this is a strong advantage with respect to the other. In addition of the area that we can cover, if we can cover 1,000 or a square degree, so we can build sample, they are not biased with respect to others. So this is also, they are very good for detection of quasar. This is 2 examples of quasar 1.6 in RESI, and this is at 2.9. And also, it is very good to do a study of Lyman alpha emitter at RESI larger than 2. I will concentrate it now only in the part of the star-forming galaxy, and I invited to Gines, who is doing the PhD with me, to explain in more detail the method that we are doing to retrieve the H-alpha and oxygen 2, oxygen 3 emission line. So please.
Here is the method we use for dealing with galaxies which have emission lines. So this method is based on neural network. So normally in the context of machine learning, we split the data between a training set. So in this case, it's CALIPHA and MaNGA survey. And also, is it not working? No? Okay, sorry. And also a test set. So our test set will be Sloan data. The idea is quite simple. Basically, what we do is we take CALIPHA and MaNGA galaxies. In these galaxies, we have measurements of the emission lines. So we have information related to the flux of H-alpha, H-beta, oxygen 3, and so on and so forth. So we take all these spectra to train the network. So what we do is we move the spectra in wavelength at a certain redshift. And at this wavelength, we compute the magnitude seen by GPass. So with the magnitude and together with the information of the emission line, we train the network. This is a schematic view of the network. So we use different configuration, but this is one network for obtaining the equivalent width of H-alpha, H-beta, oxygen 3, and nitrogen 2. Actually, we use colors rather than magnitude, because for estimating the equivalent width, the only thing that we care about is the shape of the spectrum. And we have also other network for estimating the Balmer decrement, and other one for classifying galaxies according to whether they have emission lines or not. And the criterion that we use for that is every galaxy that have an emission line in H-alpha that is greater than 3 Armstrong is considered as emitting galaxy, and everything below is not. And now I have to pass. Yeah. So here is some of the results of the simulation of this Sloan data. So we take the Sloan, we pass the filter of GPass, and we see on the top left the comparison between the neural network and what Sloan gives in terms of the equivalent width. And since we also have estimation of H-alpha, H-beta, oxygen 3, and nitrogen 2, we can compute the ratios and retrieve the PPT diagram. This is what we see on below. So on the right we have the Sloan BPT diagram, and on the left what we obtain with our method. What else? Okay, here on the left is a typical plot for classifiers in machine learning. So on the y-axis we have the true positive rate, so the amount of galaxies that we classify as emitting one, and actually they are. And on the x-axis we have the false positive rates, the rate on which sometimes we estimate that a galaxy have an emission line, but actually it's not an emission. And ideally, one would expect to have the greater area. So if we get something that is 1, is a good classifier. The blue line is something that doesn't classify. Here we have an example of a galaxy seen by Sloan, and also we have the filters of GPass. And so here we see points that are in black and in blue. The black points are all the magnitudes seen by GPass, but the neural network only work with some of the filter, not with everything, because it depends on the redshift. And what we see here is on blue the estimation that are made with our method, and in black the value measured in the spectrum of Sloan. And we see good agreement in terms of H-alpha, oxygen 3, or nitrogen 2. Of course, the emission lines that are stronger are better constrained. This is the case of H-alpha. here we do a comparison with the Aegis field. So as Rosa mentioned, we already have data. So we take this, the Aegis field and we select the galaxies that has been observed with Sloan and are at redshift below 0.35. And we compare what we get with GPAS data and with Sloan. So when we look at this plot, we see an overall agreement in H alpha, in nitrogen 2 and H beta, not in oxygen 3. But we have to take care looking at this plot because GPAS data is taking an area in the galaxy that in general is bigger than what is Sloan seen. So if we have variation of the property spatially, we cannot make a true comparison. And also, as Rosa mentioned, we have problems, not problems, but the estimation of errors has to be improved. So, you know, all these things are contributing to not make a perfect comparison. And I think that's everything. Yeah. Okay. So that one.
Okay, I will finish with the third aspect of the survey, which is GPAS as IFU survey, or low spectral resolution, of a resolution about 50. And this is the sample of result that we have obtained with the CALIFA. We can obtain most of the results that can be here, particularly those related with the stellar mass surface density, which is that plot. Also for the ages of the stellar population, and we have already seen the H alpha emission in galaxy, but also another line as nitrogen 2, hopefully oxygen 3. But of course, we cannot make a really kinematic study. But we have already obtained for CALIFA that the galaxy have grown their mass inside out. They came from the radial structure of the ages of the stellar population that decrease inside out, but also for the cumulative mass fraction, where we see that there is the increase in the inner part of the galaxy is significantly larger, quicker, faster than in the outer part of the galaxy. This is some of the results obtained, and we can test, or we can improve and go with the larger sample with the GPAS. Unfortunately, the GPAS field it is not the best field to test this kind of data and analysis, but we were lucky in the fact that we have found a bunch of galaxies which is a redshift less than 0.1, which is in the Aegis field, and we see that they can be spatially resolved. This is several examples. Now what I'm going to do is to use this galaxy and this other galaxy to show you that we can in some way do a similar work. But of course, take into account that this galaxy is significantly farther away than the CALIFA galaxy. We were lucky because also this galaxy has been observed already by MANGA. And I'll show you how we can improve the data by MANGA. Well, this is the first example. This is a spiral galaxy. That is a comparison of the data for the autophotometry, which is this correspond to this aperture. And this is the comparison with the PSF core aperture, which is smaller. And this comparison is done with respect to the Sloan. You see that for this aperture, they are significantly different to the Sloan, but no, if we take a smaller aperture. That's an indication, the fair indication that in fact there is variation of the property of the galaxy with the radial distance. We took this galaxy and we started several rings with 0.15 half-life radius, and this is 3 examples. This is the ring between 0.5 and 1 half-life radius, between 1.5 and 2, and this is the total. You see that there are H-alpha detected in all the aperture. And for the method that has explaining Ginés, we can build the equivalent. We can obtain the equivalent width of the emission line as a function of the radial distance, in addition to the stellar population property, and also the ratio of the oxygen 2 over H alpha. And this is the value in comparison with the value for the derived from the Sloan spectra. The other example that we have already analyzed is this galaxy, which is, as mentioned before, has been already observed by MaNGA. This is the only galaxy in MaNGA in the Aegis field. This is the aperture in the inner 0.5 half-large radio. That's the aperture in the 2 half-large radio. And this pentagonal is the field of view of the MaNGA. Clearly, even at this distance, we can go further in the study of this galaxy with the JPASS data in comparison with the MaNGA. Well, here it is the comparison of the spectra extracted from the MaNGA in this area, in the area that include the inner 0.5 large radio, and in black, the dot is the JPASS data. So that means that we are calibrating quite well our data in comparison, at least for this galaxy MaNGA. Also, it is included in red point the fitting with the code, the parametric code that we have I have explained before. Also, we have fitting this data with another code, no parametric code, All-Star, that has been built by Roberto C. Fernandez, and we can compare the result for the mass transforming into a star, the present mass of the galaxy, and the ages of the stellar population as a function of the radial distance. You see that the blue and the red point that correspond to the analysis of the JPASS data with different code, they are equal in the analysis, and we can compare with the MaNGA data. Look at that the MaNGA data is valid only for the first 2 rings that we are starting in this galaxy, but we can go further at distance, which is almost 0.1. So that's very, very hopefully for the survey that we can use, in fact, JPASS as a view of low spectral resolution. And that's the summary. I don't want to say too much about what I explained before, but please remember that we have a data release in the beginning of December. You are all invited to come to Teruel and to learn more about the quality of the data, and please use for your project, for your own project. And if you want to combine it with another one, it will be very, very nice for us. So thank you.
Thank you, Rob, for this seminar, and this is open for questions. Please wait the micro so the question can be recorded in the list. Questions?
First of all, thank you very much for a nice talk, Rosa. It's very enlightening. My question is related to the mass range that you cover at different redshifts with the JPASS, because you're saying that you're able to analyze galaxies up to redshift 1, but do you have an expectation of a range in masses that you're covering for each redshift?
I just, in fact, put it an histogram of the mass that we have retrieved for the 7,000 galaxy in the catalog, and that's the range of mass. They go almost from 10 to the 9 to some 10 to the 11 solar masses, which is the typical mass that we are expecting for most of the galaxy. In particular, in CALIFA, we were ranges from 10 to the 10 to this range several times to 10 to the 11 solar masses. But here we go to...
if the range is the same for every redshift.
This I don't know. Well, let me. I say no, but yes. Okay, because this is something that has been done by Luis. This is different range in redshift, and this is the stellar mass. At least the maximum of the stellar mass is quite similar. But of course, as we go to higher redshift, we cannot detect the smaller galaxy. But in terms of the higher mass, it will be similar.
Any other questions? Okay, there are no more questions. Thank you again for the speaker.